Hey everyone. So in this video I like to talk about finding the foci of an ellipse. So we've been discussing graphing ellipses for a little bit now, and we said that if we have an equation of the form x minus h squared divided by a squared plus y minus k all squared divided by b squared is equal to 1, this is the graph, or this is an equation corresponding to an ellipse centered at h comma k. And this ellipse, it's kind of like a unit circle at this center point, or centered at this center point, that's been stretched horizontally by a factor of a and stretched vertically by a factor of b. So that's how we can interpret what those numbers in the denominators represent. And so here, how can we apply those ideas to find the equation of this ellipse on the right? Well, we can see that there's a center point of 1, 1. And we can kind of see that this would be, if we were imagining taking a unit circle and stretching it out to get this ellipse, well, it would be stretched by a factor of 2 in the horizontal direction, and it would be stretched by a factor of 3 in the vertical direction. And so we can see this as coming from the equation x minus 1 squared divided by 2 squared. Right, that x minus 1 is coming from x take away the x value of this center point. And we're going to add that with y minus 1 squared, right? Y take away the y value of this center point. And that's going to be divided by 3 squared, how much this, the stretch factor in the vertical direction is equal to 1. So this is the equation of this ellipse. And so there's some other definitions or terminologies that I want to bring up regarding an ellipse. So here, oftentimes you'll hear people talk about the major axis of an ellipse and the minor axis. So the major axis is really just this sort of line segment here in this picture. This would be the major axis here. It's sort of the longest line segment you can fit inside of an ellipse. It goes along that vertical direction here because we've got this ellipse is stretched more in the vertical direction than in the horizontal direction. So the major axis is the longest line segment that you can fit inside an ellipse, running along the direction it's been stretched the most. And the minor axis well, this is the shortest line segment inside an ellipse. And in this case, it's this line segment here, going horizontally. This is sort of the smallest line segment we can fit inside this ellipse, and it runs along the direction in which we've stretched our ellipse at sort of the smallest amount. So here, because we've stretched our graph or our ellipse vertically by a factor of 3, and we've stretched our ellipse horizontally by a factor of 2, our minor axis is along where we stretched horizontally, because we've stretched that smaller than vertically. So for every ellipse, there's two special points associated with that ellipse. That they fall on the major axis, and we call these two special points the foci. This is a plural of the word focus. So if we're trying to talk about just one of these points, we'll call it the focus, and if we're trying to talk about both of these points, we'll call them the foci. And so what's special about these 2 points? Well, if we take any point on our ellipse and we measure the distance between that point and these 2 foci, and we add those distances together, we'll get the same amount no matter what point we started with on our ellipse. And so that's a pretty full definition, but let me just illustrate here. So I've got an ellipse and its 2 foci, And I guess what I'm trying to say is that if we look at a point on this ellipse and we measure the distance between that point and the foci, so there's one distance d1, and here's maybe another distance d2 between our point and the two foci. This is going to add up d1 plus d2. Those two distances, when we add them together, they're going to come out to the same amount as if we were to pick a different point on this ellipse and measure their distances between the two foci and add those up. So here, if I look at this point on the ellipse and measure the distances between that point and the foci, so d3 and d4 maybe, and there are going to be different amounts than the previous two distances, but when we add them together, we get the same amount. So I guess what I'm trying to say is, if we take d1 plus d2, this is going to be the same as d3 plus d4. Doesn't matter what point on our ellipse we choose, the sum of these two distances will always be the same amount. So I want to take a look at how the location of the foci on the major axis, how these locations relate to the quantities a and b. Right? So these are the numbers that tell us how much we stretch our ellipse in the horizontal direction and how much we stretch our ellipse in the vertical direction. And maybe to have something a little bit more concrete to visualize, let's just look at the scenario where the major axis is horizontal. Right? The direction we've stretched our ellipse is larger in the horizontal direction. And so what this means is that if we're looking at an equation, we're looking at one where that quantity a, that's dividing that x minus h squared, that quantity a is larger than our quantity b, that's dividing our y minus k squared. We're stretching more in the horizontal direction than the vertical direction. That's what I want to visualize and talk about first. And also, maybe for the sake of simplicity, let's really just think about an ellipse that's centered at the origin. Right? So here, we're really looking at this picture of x squared over a squared plus y squared over b squared is equal to 1, where a is greater than b. And so here I've got that ellipse drawn out, where here we can kind of see that these points, usually called the vertices of an ellipse, these would be a comma 0, right? This distance here is supposed to be a. And if we're looking at this ellipse being centered, then a units to the right would be that vertex. And then here this distance is supposed to be b. And so we can see that this point ought to be 0 comma b. This point ought to be negative a comma 0, and this point ought to be 0 comma negative b. And so something I didn't mention earlier is that the foci, right, they lie on our major axis, and they lie the same distance on either side of this center. So maybe we can call this distance c. So I want to explore that distance for now. So we can say that these points here would be c comma 0 and negative c comma 0, right there. C units to the right of the origin and c units to the left of the origin. And so here we were saying that no matter what point we take on our ellipse, we should get the same distance, or we should, when we add those distances between that point and the foci, we get the same amount every time. And we can look at the point where we're at a comma 0. What distances do we get between the foci and this point? Well, this distance here, from negative c comma 0 to a, well, this is a distance of a. This is a distance of c. And so the distance from one foci to that point a comma 0 is a plus c. And if we add that on with the distance from the other foci to our point on the ellipse, right, this distance here, well, that distance is, we know that this entire distance here would be a, and the distance that we're missing is c. And so that remaining orange distance there, that's a minus c. And in other words, this is equal to, well, we've got 2a and then c minus c comes out to be 0. So we just have 2a is the distance, the sum of the distances between any point on this ellipse and the foci, yeah. So that's, maybe I'll draw it out one more time. That's this distance added on with this distance. And so if we go through the same motions again, but maybe we pick a different point that stands out, maybe let's pick this point up here, and we look at the distance between that point and one focus and the distance between that point and the other focus, and we add those two distances up. They should give us the same distance, or the same sum as what we got a moment ago, 2a. And so here, this point we said was the point 0, comma b. And we said this point is negative c, comma 0, and c, comma 0 here. Well, I can notice that there's this right triangle here. And the distance we're trying to find is the hypotenuse of that right triangle. And so here, one of these distances, maybe this distance on the right side, well, that can be computed by finding the hypotenuse of the triangle with side length c and side length b. Right, in other words, this quantity, if I called this d1 and d2, well, d2 would equal, well, maybe I should say, using the Pythagorean theorem, d2, if we were to square this would be the same as b squared plus c squared. And so this distance d2 is equal to the square root of b squared plus c squared. So that's the distance d2, and we want to add that with the distance d1. But really, we get the same picture here, right? What's the side lengths of this right triangle? Well, this is a side length of c, and this is a side length of b. And so d1 squared, by the Pythagorean theorem, that is the same as b squared plus c squared. And so d1, that distance between one focus and the point on our ellipse here, is the square root of b squared plus c squared. And so the sum of these two distances, d1 and d2, well, here that's the square root of b squared plus c squared plus the square root of b squared plus c squared. And if I take two of the same things and I add them together, no matter what that quantity is, well, that's really the same as 2 times that quantity that's being added with itself. Right? Really, you can kind of picture this as if I took x plus x, this is the same as 2x. And so if I take this quantity plus itself, well, that's the same as 2 times that same quantity. And so we're saying that this distance here, or the sum here should be the same as the sum we got above, right? That's the definition of an ellipse, is that I take any point on our ellipse, we add up the distances between that point and the two foci, we'll get the same amount every time. And so here, 2a ought to be the same as 2 times the square root of b squared plus c squared. And so maybe I'll write that down here. We know that 2 times a needs to be equal to 2 times the square root of b squared plus c squared. And so if we were to divide both sides by 2, we would cancel out that factor of 2. Right, so we still have this a is equal to the square root of b squared plus c squared. And we're looking for this distance, right, for between the center and the focus, the foci. Right, that's this value c. We want this value c here. Right? And again, A represents the amount that our ellipse has been stretched horizontally. B represents the amount our ellipse has been stretched vertically. And so let's get that C variable alone. And we can do that by squaring both sides. Right? If I square the right side and I square the left side, what we get is A squared. This is equal to B squared plus C squared. And then right, we're trying to get C closer to being alone. We get, after subtracting both sides by B squared, we get A squared minus B squared is equal to C squared. And so maybe I'll write this without colors one more time. And we can talk about what this means here. So C here, this is the distance between the foci and the center of our ellipse. And here A, this was the distance, or the amount we stretched our ellipse horizontally. And this was the stretch along, really the thing I want to emphasize here is that, what's special about the horizontal stretch in this case was that was the stretch along our major axis, the larger stretch for our ellipse. So this was the stretch along the major axis. In this case, that was horizontal. And then B, well, this is our stretch of our ellipse along the minor axis. And in this case, this is vertical. And so if we're ever trying to find the foci on our ellipse, we just have to use this relationship here between the stretches to find the distance between the center and the foci. And so what we're really saying here is if we look back up at our picture, maybe I'll erase some of these measurements here. Right, so this distance C from the center, this distance C from the center of our ellipse to one of the foci, right? So this is C, and we're saying that really it's given by the relationship C squared is equal to A squared minus B squared, where A is this measurement here, and B is this measurement here. And so all the reasoning that we had for determining the location of the foci in our previous example, right, this was all based on the fact that we stretched our ellipse more horizontally than vertically. But really we can take all this reasoning and apply it more or less the same way to situations where we stretch more vertically than horizontally, and really we come out with sort of a symmetric idea that if our ellipse has been stretched more vertically than horizontally, in other words, B is greater than A, then really we can take B squared minus A squared to get C squared and find the distance between the center and the foci. Right, so here again, this is the stretch along the major axis. In this case, it's vertical. And here A is the stretch along the minor axis. And in this case, it's horizontal, and this gives us the distance, or lets us compute the distance between the center and the foci. Along our major axis. And so let's apply this idea of finding the foci to our ellipse we started with at the beginning of this video. So here the major axis is in the vertical direction. this ellipse has been stretched by a factor of 3 in the vertical direction, and the minor axis, so along our horizontal direction, it's been stretched by a factor of 2. And so here, if I want to find the foci, well, I can use a relationship that 3 squared take away 2 squared is equal to c squared. And so this gives us 9 minus 4 is equal to c squared. In other words, c is equal to, well, 9 minus 4 is 5. Maybe I'll write down this extra step. So 5 is equal to c squared. And so c is equal to plus or minus the square root of 5. And so in this picture, where are the foci? Well, we take our center point and we look this many units along the vertical, along the major axis away from the center. So here, if I look the square root of 5 units, so that's a little bit more than 2 units away from the center in the vertical direction. So maybe here, this distance is the square root of 5, and if I look downwards as well, a little more than 2 units, with this distance being the square root of 5, we get our foci. And the idea is that the distance between any point on the ellipse and these 2 points, if we add them together, we're going to get the same result every time. And so what are these points here? So the foci, well, they have the same exposition in all 3 of these points, the foci in the center. They all have an exposition of 1. But what's the y position? Well, the top point, it's 1 is the y position plus the square root of 5, right? We're adding the square root of 5 on top of that y value of 1. And then 1 comma 1 minus the square root of 5 is the location of that second point below. And so what if we want to find an equation of an ellipse where we know the foci and we know, let's say, the length of the major axis? Well, here we're saying that the foci are located at 5, 0 and negative 5, 0. So maybe those are these points here, right? So 5, 0, negative 5, 0. And so because we can see that those 2 points lie on the line, the horizontal line, y is equal to 0, we can see that our major axis should be horizontal. Right? So here we're saying that there should be a major axis that is 12 units long in total. It should be 12 units. And so it's telling me that really my ellipse, I can imagine, is being stretched by a factor of 6 in the horizontal direction. And so this the point out here is 6, 0 and negative 6, 0. And my ellipse should look something like this. I mean, we don't know exactly where the vertical stretch is, and that's something we need to figure out. But maybe just have a picture in mind. I think this can help. And so we know that here, if we take the stretch along the major axis, in this case the horizontal stretch, a squared, we subtract away the stretch along the minor axis, in this case the vertical stretch, b squared, we should get our foci distances squared from our center. And so here, the horizontal stretch, well, that's 6 squared. We don't know the vertical stretch. And the foci, well, that's this distance between the center and the focus on the right, that's 5 units. So I could write this as 5 squared. And so we get 36 minus b squared is equal to 25. Subtracting 25 from both sides, we get 11 minus b squared is equal to 0, telling us that 11 is equal to b squared. And so that means b is equal to plus or minus the square root of 11. So that's this distance here is the square root of 11. And so that tells us everything we need to know, right? If we're talking about an ellipse that's centered at the origin, then we've got x squared divided by the horizontal stretch, that's 6 squared, plus y squared divided by the vertical stretch, well, that's the square root of 11 squared is equal to 1. And we could rewrite this as x squared over 36 plus y squared over 11 is equal to 1 if we prefer to get rid of that square root. But this is the equation of our ellipse.